Why spacecraft were built with known flaws. There is a common assumption about spacecraft that if something was flawed, it must have been overlooked. That if a weakness existed, it must have been missed. That engineers would never knowingly send people into space inside a system they knew was imperfect. That assumption is wrong. Many of the limitations built into early spacecraft were not accidents. They were identified, documented, discussed, and deliberately carried forward. Engineers knew where systems were fragile. They knew which margins were thin. They knew which components behaved reliably only within narrow bounds. Those flaws were not hidden. They were tracked. Test data exposed them. Simulations revealed them. Reviews documented them. In some cases, the behavior of a system outside ideal conditions was understood in detail long before flight. The question was never whether the flaw existed. The question was whether the system could be operated safely with it. In complex machines, fixing a flaw is rarely a simple act. Changes propagate, interfaces shift, new failure modes appear. A correction in one place often introduces uncertainty somewhere else. By the time spacecraft reach late stages of development, stability itself becomes a form of safety. A known weakness can be planned around. An unknown consequence cannot. This logic did not belong to one program or one era. It appeared across human spaceflight, in different vehicles, under different pressures. Apollo made it visible because of the stakes involved, but it was never unique. In many cases, engineers faced a choice between an imperfect system they understood deeply and a modified system they understood less. The safer option was not always the one that looked better on paper. What mattered was predictability. A flaw that behaved the same way every time could be managed. A system that changed late in development could not be fully relearned before flight. The cost of fixing something was not measured only in hardware, but in lost familiarity, retraining, and new uncertainty. This is why some spacecraft flew with limitations their designers openly acknowledged, not because the flaws were acceptable in the abstract, but because the alternatives carried risks that were harder to see, harder to bound, and harder to control. Spacecraft were not built to be perfect. They were built to be understood well enough to survive. This episode is about that reality, not about mistakes that slipped through, but about weaknesses that were known, weighed, and accepted, and why, in some of the most demanding engineering environments ever created, that choice was often the safer one. Part 1. What flaw meant in spacecraft design. In everyday language, a flaw is a mistake. It implies something was missed, something should have been corrected, something went wrong that ought to have been caught earlier. In spacecraft design, the word means something very different. A flaw is not necessarily an error. It is a condition, a boundary, a behavior that exists under certain circumstances and does not under others. It is something the system does reliably, even if that behavior is undesirable. Engineers draw a sharp distinction between a system that behaves badly and a system that behaves unpredictably. An unpredictable system is dangerous. A predictable one can be managed. This distinction matters because complex machines never behave perfectly across all conditions. Materials expand and contract. Sensors drift. Power systems fluctuate. Software interacts with hardware in ways that are sensitive to timing, load, and environment. The question is not whether these behaviors exist. It is whether they are understood. In spacecraft development, a flaw often referred to a known limitation that appeared consistently in testing. A thermal region that ran hotter than ideal. A power margin that narrowed during specific phases. A component that performed reliably, but only within a defined operating envelope. These were not surprises. They were characteristics. Designers documented them, measured them, and learned how they behaved over time. A flaw that appeared the same way in test after test was often considered safer than a theoretical improvement whose real-world behavior was uncertain. This is where intuition breaks down. Outside engineering, improvement is assumed to reduce risk. Inside complex systems, change often introduces new uncertainty. A modification intended to remove a flaw alters interfaces, timing, and interactions, sometimes eliminating one known problem while creating several unknown ones. Engineers, therefore, classify flaws differently from failures. A failure is a condition where the system no longer performs its required function. A flaw is a condition where the system performs its function with constraints. Those constraints matter operationally, but they do not necessarily prevent mission success. For example, a system that must be operated more slowly during certain phases is flawed in the sense that it is limited. But if that limitation is consistent and understood, procedures can be written around it. Training can incorporate it. Crews can anticipate it. A system that sometimes behaves normally and sometimes does not is far more dangerous. This is why predictability often outranks optimization. A design that performs slightly worse, but always the same way, allows organizations to build habits, rules, and expectations around it. A design that performs better on average, but changes behavior after modification, requires the entire system to relearn itself. In late-stage spacecraft development, that relearning carries cost. Every change demands new testing. Every test demands time. Every hour of testing consumes schedule margin and introduces opportunities for new discrepancies. Verification becomes harder as the system grows more complex. As a result, engineers learn to ask a different question. Not, is this system perfect? But do we understand it well enough to operate it safely? A flaw that can be bounded, monitored, and anticipated becomes part of the system's operating model. It shapes procedures. It influences training. It informs mission rules. This does not mean engineers are indifferent to imperfections. It means they are realistic about trade-offs. The worst outcome is not flying with a known limitation. The worst outcome is changing a system late and losing understanding of how it behaves under stress. In spacecraft design, safety is not only a function of hardware quality, it is a function of familiarity. Systems that crews and controllers understand deeply can be managed even when they are imperfect. Systems that change faster than people can adapt become fragile. This is the lens through which flaws must be understood, not as mistakes waiting to be corrected, but as conditions that shape how the system is used. With that understanding in place, the next question becomes unavoidable. Why did attempts to fix flaws so often make things worse? Part 2. Why fixing a flaw often made the system worse. In isolation, a flaw looks like a problem to be solved. A component underperforms. A margin is thinner than desired. A behavior deviates slightly from expectation. On paper, the response seems straightforward. Improve the part. Adjust the design. Add capacity. Tighten tolerances. In complex systems, that logic rarely holds. Spacecraft are not collections of independent components. They are tightly coupled assemblies where every change interacts with multiple subsystems at once. A modification intended to correct a single issue alters mass, power draw, thermal behavior, timing, and interfaces. Those changes ripple outward, often in ways that are difficult to predict in advance. A fix is never just a fix. It is an intervention into a system that has already learned how to behave. Late in development, spacecraft exist in a fragile equilibrium. Hardware has been built, tests have been run, procedures have been written. Crews and controllers have trained against specific system responses. Even small adjustments disrupt that equilibrium. Consider what happens when a component is replaced to address a known limitation. The new part may perform better in one dimension, but it changes the system's overall behavior. It may draw power differently. It may produce heat in a different location. It may respond faster or slower than the original. Those differences affect sensors, software timing, and the assumptions built into operational procedures. Each interaction must be reevaluated. That evaluation is not theoretical. It requires testing. Testing requires time. Time is finite. As schedules tighten, verification becomes more selective. Engineers focus on confirming that the change does what it is supposed to do. But it is impossible to retest every interaction in the same depth as the original system. Some behaviors remain unobserved until flight. This is where fixes become dangerous. A known flaw has known boundaries. A modified system has unknown ones. Engineers understand this intuitively. That understanding creates hesitation, not complacency. The reluctance to just fix it comes from experience with unintended consequences. In spacecraft development, history is filled with examples where improvements introduced new failure modes that were harder to diagnose and harder to manage than the original issue. A fix can also shift risk rather than reduce it. Increasing redundancy adds components, wiring, and interfaces. Each additional element increases complexity and the chance of interaction errors. Redundancy protects against certain failures, but it can introduce ambiguity when systems disagree about which state is correct. Similarly, increasing performance margins often increases stress elsewhere. Higher power availability demands greater thermal rejection. Higher thrust load structures differently. Higher computational capacity requires more complex software, which in turn increases verification burden. Every gain carries a cost. Engineers therefore evaluate fixes not only on whether they address the immediate issue, but on what they destabilize. A change that removes a flaw but forces widespread retraining, procedural updates, and partial re-verification may increase overall system risk. The organization must relearn how the spacecraft behaves, often under compressed timelines. That relearning is not instantaneous. Crews build intuition through repetition. Controllers develop pattern recognition through exposure. Procedures evolve as anomalies are encountered and resolved. All of that knowledge is anchored to a specific system configuration. Change the system late, and much of that learning becomes obsolete. This is why engineers often prefer to live with a limitation they understand rather than adopt an improvement they cannot fully characterize before flight. The decision is not driven by conservatism alone, it is driven by respect for complexity. Complex systems fail not because they contain weaknesses, but because those weaknesses interact in unexpected ways. Stability allows organizations to map those interactions over time. Frequent change prevents that mapping from ever converging. In practice, this means that fixes are evaluated against a different standard late in development. Early on, improvement is encouraged. Designs are fluid. Alternatives are explored. Trade-offs are still negotiable. Later, the bar rises sharply. A fix must not only be better, it must be safer to introduce than to ignore. That is a high threshold. Most proposed changes fail to clear it. The result is a counterintuitive outcome. Systems fly with known flaws, not because engineers accept imperfection lightly, but because they understand how risk accumulates through change. Fixing a flaw is not about eliminating a weakness. It is about deciding whether the system can absorb the consequences of intervention. Often, the answer is no. This does not mean flaws are forgotten. They remain visible. They are tracked, monitored, and incorporated into operational planning. But they are no longer treated as defects to be removed. They become constraints to be managed. At this point, the nature of engineering work shifts. The focus moves away from redesign and toward operation, away from modification and toward discipline, away from improvement and toward understanding. That shift is not a failure of ambition. It is an acknowledgement of reality, and it leads directly to an uncomfortable realization that good enough may be safer than better. This moment is not announced. It does not arrive all at once. It emerges gradually as people realize that every proposed improvement carries consequences the system may no longer be able to absorb. At that point, the meaning of safety begins to shift. Early in development, improvement reduces risk. Designs are flexible, testing is broad, mistakes are expected and corrected. Change is how understanding grows. Later, improvement begins to compete with familiarity. By the time spacecraft approach readiness for flight, the organization has invested years learning how a specific system behaves. Engineers know which readings fluctuate and which ones matter. Controllers recognize patterns that do not appear in documentation. Crews develop intuition about timing, feel, and response. That knowledge is fragile. It is built slowly and lost quickly. A change that improves performance but alters behavior forces the organization to start relearning under pressure. Training must be revised. Procedures must be updated. Simulations must be rebuilt. Experience accumulated against the old configuration becomes less reliable. The system becomes new again. In that context, better is not always safer. Engineers face an uncomfortable trade-off. Carry a limitation they understand, or introduce a change that requires rediscovering how the system behaves when it is stressed. This is not an abstract decision. It involves professional judgment, accountability, and personal responsibility. Engineers are aware that the system they sign off on will be flown by others. That awareness encourages caution, not complacency. Accepting a known flaw does not feel like settling. It feels like stewardship. The goal becomes preserving the integrity of understanding, protecting the shared mental model that allows teams to respond coherently when something deviates from plan. In this phase, discipline replaces optimism. Constraints are respected. Boundaries are enforced. Behavior outside expected ranges is treated seriously, not because it is surprising, but because it is understood. Good enough becomes a technical position, not a slogan. It reflects the belief that a system everyone understands deeply is safer than a system that is theoretically superior but incompletely known. This is why spacecraft often fly with limitations that appear uncomfortable from the outside. Those limitations are not blind spots. They are deliberate choices made in recognition of how complex systems actually behave. At this point, the question is no longer whether flaws exist. The question is how they are lived with. And that shifts the story away from design and toward operation. Part 3. Flaws that were actively managed, not corrected. Once a flaw was accepted as part of the system, it did not disappear. It changed roles. A limitation that could not be redesigned became something that had to be managed continuously. It moved out of the design space and into operations, training, and decision-making. The work shifted from eliminating the flaw to shaping behavior around it. This is where the character of the system became visible. Known flaws were rarely treated as static defects. They were treated as conditions that required attention, discipline, and restraint. Their presence influenced how systems were used, when they were stressed, and under what circumstances margins were intentionally protected. Operational rules emerged directly from these limitations. If a component behaved unpredictably under certain loads, those loads were avoided. If a thermal region became unstable during specific mission phases, procedures were written to limit exposure. If a system degraded gradually rather than failing outright, monitoring protocols emphasized trends over thresholds. These responses were not improvised, they were formalized. Mission rules captured what was allowed and what was forbidden. Procedures specified not only what to do, but what not to do, and when inaction was safer than intervention. Constraints that existed in hardware were mirrored in operations. Training reinforced this discipline. Simulations were designed to expose crews and controllers to known edge cases repeatedly, not so they could memorize responses, but so they could recognize familiar patterns when they appeared under pressure. A flaw that behaved consistently became something people could anticipate rather than fear. This familiarity mattered. In high-stress environments, recognition is faster than analysis. A controller who has seen a specific pattern dozens of times does not need to debate whether it matters. A crew that understands the boundaries of a system does not push it into regions where behavior becomes ambiguous. Flaws were also managed through pacing. Operations were often designed to move deliberately through phases where margins were thin. Systems were allowed to stabilize before being asked to perform again. Tasks were sequenced to avoid compounding stress on components known to be sensitive. This kind of restraint is easy to overlook. From the outside, it can appear conservative or inefficient. From the inside, it is a form of risk management that prioritizes predictability over speed. In some cases, limitations shaped mission architecture itself. Activities were scheduled around periods when systems were most reliable. Contingencies were planned to allow graceful degradation rather than abrupt failure. Secondary objectives were abandoned if they threatened to push hardware beyond well-understood limits. The presence of flaws also influenced how authority was distributed. When systems were known to behave poorly under certain conditions, decision-making was often centralized to avoid conflicting actions. Conversely, when behavior was well understood but time-sensitive, authority was delegated to those closest to the data. These choices reflected confidence in understanding, not fear of failure. Importantly, flaws were never managed in isolation. Their interactions mattered more than their individual characteristics. A thermal limitation might be manageable on its own, but problematic when combined with power constraints. A sensor drift might be acceptable unless paired with software timing sensitivity. Operations teams learned to think in combinations rather than components. This holistic view was cultivated deliberately. Controllers were trained to consider how changes in one system might affect others, even when no explicit failure had occurred. Crews were encouraged to report subtle deviations, not because they demanded immediate action, but because they contributed to a shared picture of system behavior. Over time, the system developed a kind of operational personality. Certain behaviors were expected, certain responses were trusted, certain anomalies were tolerated because their consequences were understood. Others triggered immediate attention because they violated established patterns. This does not mean the system became complacent. It became selective. Attention was focused where it mattered most. Noise was filtered. Energy was conserved for moments when judgment, not procedure, would be required. This is how flaws were lived with, not by ignoring them, not by normalizing danger, but by integrating limitations into the daily rhythm of operation. The spacecraft was not treated as an idealized design. It was treated as a real machine with specific habits, sensitivities, and tolerances. That realism made discipline possible, and it exposed a crucial vulnerability. When flaws are acknowledged and managed, they strengthen operational awareness. When flaws are hidden or dismissed, they become traps. That distinction leads to the next question. What happens when organizations pretend flaws do not exist? Part 4. The cost of pretending flaws don't exist. A known flaw is not the most dangerous thing a system can carry. An unacknowledged one is. When limitations are documented, tracked, and discussed openly, they shape behavior. They inform training. They influence decisions about when to act and when to wait. People adjust their expectations to match reality. When flaws are minimized, obscured, or reframed as non-issues, the system becomes brittle. This brittleness does not appear immediately. It accumulates quietly through small mismatches between how the system actually behaves and how people believe it behaves. Denial takes many forms. Sometimes it is optimism, a belief that a limitation will not matter in practice. Sometimes it is normalization, a tendency to reinterpret recurring anomalies as acceptable noise rather than signals. Sometimes it is pressure, an incentive to present systems as more capable than they are in order to maintain confidence, funding, or schedule. None of these feel reckless in isolation. Together, they distort judgment. When organizations stop talking openly about limitations, they stop planning around them. Procedures drift away from reality. Training scenarios no longer reflect the full range of behavior. New team members inherit simplified narratives that omit uncomfortable details. Over time, understanding erodes. The danger is not that flaws exist. It is that people are surprised by them. Surprise is what overwhelms systems under stress. It compresses decision time. It forces improvisation where preparation should have existed. It pushes people to act based on incorrect assumptions. In complex systems, surprise is often fatal. Pretending flaws do not exist also encourages overconfidence. When systems are described as more robust than they truly are, operators may push them harder than intended. Margins are consumed unknowingly. Interactions that were once avoided become routine. The system is asked to perform closer to its limits more often and with less hesitation. Eventually, behavior crosses a threshold. A limitation that was manageable when respected becomes dangerous when ignored. A constraint that was safe when visible becomes hazardous when forgotten. This is how failures propagate. Not through a single overlooked defect, but through a gradual divergence between reality and belief. Importantly, denial does not require malice. It can arise from success. When systems perform reliably for long periods, confidence grows. Anomalies that do not lead to immediate consequences are discounted. Attention shifts elsewhere. The absence of failure is mistaken for the absence of risk. This is why transparent acknowledgement of flaws is a form of safety. It anchors expectations. It keeps attention calibrated. It prevents the slow drift toward assumptions that no longer hold. Organizations that manage known flaws well develop a habit of skepticism. They question reassuring signals. They treat deviations seriously even when outcomes are favorable. They resist the urge to simplify narratives at the expense of accuracy. This discipline is difficult to maintain. It requires accepting discomfort. It requires admitting limits. It requires resisting the temptation to promise certainty where none exists. But the alternative is worse. Systems that pretend to be better than they are invite misuse. They encourage decisions that rely on capabilities the system does not consistently possess. They collapse when reality asserts itself. This is not unique to spaceflight. It is a general property of complex, high-consequence systems. When flaws are acknowledged, they can be managed. When they are denied, they become traps. Understanding this distinction brings us to the final question of the episode. Why did flying with known flaws often make spacecraft safer, not more dangerous? Part 5. Why known flaws can make systems safer. At first glance, the idea seems backward. A system with flaws should be less safe than one without them. A spacecraft with limitations should be more dangerous than one that performs flawlessly across all conditions. In practice, the opposite is often true. Safety in complex systems does not come from eliminating every weakness. It comes from aligning expectations with reality. A system that behaves imperfectly but consistently allows people to prepare for what it will do under stress. Known flaws create boundaries. They define where behavior changes. They mark regions of uncertainty. They signal when caution is required and when confidence is warranted. When those boundaries are clear, operators adjust naturally. They slow down. They monitor more closely. They avoid pushing the system into ambiguous territory. This calibration is a form of protection. A system that appears flawless encourages risk-taking. It invites operators to assume margins that may not exist. It hides the points where behavior shifts from stable to unpredictable. In contrast, a system with visible limitations keeps attention engaged. Crews and controllers who understand where a spacecraft is weak develop habits that compensate for those weaknesses. They anticipate rather than react. They recognize early signs of deviation. They treat certain readings with appropriate skepticism instead of blind trust. This does not make operations easier. It makes them safer. Known flaws also shape training in ways that improve resilience. When limitations are acknowledged, training scenarios can be built around them. Crews are exposed to edge cases repeatedly. Controllers practice decision-making in constrained conditions. Judgment is refined in the presence of real boundaries, not idealized assumptions. This produces confidence grounded in experience, not optimism. Importantly, known flaws reduce surprise. Surprise is the enemy of safety. It compresses time, overwhelms attention, and forces decisions to be made without context. Systems that behave differently than expected erode trust at the moment it is needed most. When a flaw is known, its appearance does not shock the organization. It triggers recognition. Recognition leads to action that is measured rather than impulsive. This is why predictability matters more than perfection. A perfectly performing system that fails unpredictably is far more dangerous than an imperfect system that fails in familiar ways. The former leaves no room for preparation. The latter allows organizations to build responses that are tested, rehearsed, and understood. This logic applies not only to hardware, but to organizations themselves. Teams that openly acknowledge limitations maintain sharper situational awareness. They resist complacency. They question reassuring narratives. They retain humility in the face of complexity. These qualities are protective. Flying with known flaws does not mean accepting unnecessary risk. It means choosing the risks that can be seen, understood, and managed over those that cannot. It reflects an understanding that safety is not a static property of a machine. It is an emergent property of how people interact with that machine over time. In spaceflight, success has often depended less on flawless design than on disciplined operation, less on eliminating every weakness than on knowing exactly where those weaknesses are. This is the quiet lesson that runs through the history of spacecraft design. The systems that survived were not the ones that promised perfection. They were the ones that invited understanding, and that understanding made all the difference. Part 6. What? These flaws quietly revealed. Spacecraft were never meant to be flawless. They were meant to be survivable. That distinction matters because it shifts attention away from what systems are supposed to be and toward how they are actually used. In environments where failure carries real consequences, safety does not come from pretending limitations do not exist. It comes from building organizations that can operate honestly inside them. The history of spaceflight shows this repeatedly. Design decisions produced machines with boundaries. Engineering trade-offs created systems that performed reliably in some regions and poorly in others. Those limitations did not disappear with time. They followed missions into flight. What determined success was not whether flaws existed, but whether people understood them. Programs that acknowledged imperfections learned how to manage them. They shaped training around real behavior. They wrote procedures that reflected actual constraints. They distributed authority and attention in ways that matched how systems failed, not how they were supposed to work. This did not eliminate risk. It made risk legible. Legible risk can be monitored. It can be discussed. It can be prepared for. Illegible risk arrives as surprise, and surprise is what overwhelms complex systems. This is why flying with known flaws was often safer than chasing late-stage improvements. The cost of change was not just hardware, it was lost understanding, it was broken intuition. It was the erosion of shared expectations that allowed teams to respond coherently under pressure. Spacecraft that succeeded did so because people knew them deeply. They understood their habits, sensitivities, and limits. They did not confuse ideal performance with real behavior. That lesson extends beyond spaceflight. Any system built under constraint will carry imperfections forward. What matters is whether those imperfections are treated as embarrassments to be hidden or realities to be managed. The programs that endured chose the second path. They accepted that safety is not achieved by eliminating every weakness, but by making weakness visible enough to shape behavior. That is what allowed imperfect systems to work. In the next episode, we will step back from individual spacecraft and look at the broader trade-offs that defined early spaceflight and how entire programs were shaped by what they chose to give up. Subscribe to continue exploring how complex systems actually function when ideal options are not available. Each episode examines one set of constraints and the structures built to live inside them.